Welcome, Saral.
I hope everyone can hear me. Yeah? Okay. Well, it's a privilege to be here and sharing our team's work. My name is Saral. I'm here with Ranjit. We work on the traffic infrastructure team at Facebook. We're here to talk about Proxygen Mobile, our cross-platform native networking library, which enables our apps to leverage the network more effectively. It's built on top of Proxygen, our framework for, this would be helpful, our framework for building high-performance proxies. It supports speedy, HTTP2, TCP, and others. Before we get into the networking stack, which Ranjit will do shortly, my goal in the next 10 minutes is to share with you our observations of various network conditions around the world and some key points which led us to Proxygen Mobile. I hope with the information we share today, we can help you build apps that are more resilient and fast to ever-changing network conditions. Success. Mobile networks. They can be very different all over the world. They've emerged over time, and they tend to have different properties. They seem to have grown organically as new technologies have emerged. It can be very difficult to gauge what's going on in the network without the right set of tools. There are many network constraints. To help us understand some of these network constraints, let's dive into the network profile based on the usage of our mobile apps around the world. As you can see here, there are many sessions that are primarily based on Wi-Fi. About 30% of them are on mobile. And interestingly so, 5% of these sessions over time are when there is no network connectivity. So what does this tell us about each country? We work really hard to make sure that our app works for everyone around the world, in all the countries, every place in the world. So let's slice this data by country to see how this data is specific to a country or not. And you see a pattern emerging for developed countries where there is easy Wi-Fi access, such as United States and Britain, that you see high number of sessions being established on Wi-Fi. Further to the right or left, emerging markets such as India and Nigeria tend to not have easy Wi-Fi access. You see a large number of sessions being established on mobile. So there is no unique pattern that you can say globally that these patterns apply to all countries and so on and so forth. Every country is unique. So how do we understand more about some of the network constraints? So let's dive into some of the technologies our apps are seeing around the world. Around the world, you see high penetration of LTE and a lot 3G, which means that apps running on these technologies will see higher bandwidth, lower latency, relatively speaking. But that's not true for every country. If you compare this data with the data from India, you will see that in India, there is a high penetration of the 2G networks. That means lower bandwidth and higher latencies. But understanding technology is not enough to understand speed and performance. We've all been here. We have the best of devices, the latest and the greatest networks, full bars on our device, but still the app doesn't work. Why is that? The earlier talk talked about some of the great innovations you can do on the app layer. We'll concentrate on the network layer. So what can be going on? Are you changing cell towers? Is the bandwidth underneath you changing? Are you egressing from a mobile net hundreds of miles away from you, connecting to a data center thousands of miles away from you? Is the network getting crowded? Are your latencies spiking? Do you even have the right data plan? How long is it taking for the phone radio to connect to the tower? All of these things influence the network. And it can be very hard to build apps in these situations. We need new tools which allow us to measure and react to the changing environment. To better understand some of this variability, let's see how bandwidth and latency vary across the world by technology. Facebook open sourced the network connection class earlier this year, which enables our apps to estimate what is the available bandwidth at any given time. Based on that, you can see that Wi-Fi does not mean consistent speed everywhere in the world. In India, Wi-Fi is much slower than in Britain. Focusing on the latest mobile technology, LTE, the one in between, you see that there is a large spread there as well. Furthermore, if you were to focus on speed in emerging markets, the bandwidth in Brazil is 3 times slower than in Britain. Sorry, I skipped that slide. But latencies are another issue that you need to take into account. Latencies are, as manifested in this graph, are round-trip times around the world for various network technologies. The green bar shows the round-trip times on edge, the yellow in 3G, and then the last one, the blue on Wi-Fi. As you can see, there is a wide spread here. If you want to build an app that works really well in Nigeria, where the round-trip times are around 2.7 seconds, if the customer has to launch your app and you fetch the data on the network, there's going to be a lot of time being spent. Maybe some strategies that we talked about earlier, including prefetching and sending less data, would be helpful in these conditions. Here's a graph of variability of latency on edge in India. Edge, as I mentioned earlier, is the dominant network in India. This is what people experience all through the day. The spikes here are in the evening times when more people get on the network. And you see latency spiking by 1 second. So during the day, the latencies are, or the round-trip times are 1.32 seconds. And later in the day, they go up to 2.32 seconds. So all of this means that building apps in these situations can be hard. Observability is key to reason what's going on in the network. These network constraints need to be solved across multiple platforms. We need to solve them for both Android, iOS, and other places where our apps run. But we are not solving them consistently because on Android, we write our code in Java, on iOS, Objective-C, so bugs are different on two platforms. We performance tune separately. That means we're spending a lot of time doing the same things over and over again. So what does this all mean from a product experience perspective? So let's take this example of streaming video, and let's see what are some of the product experience decisions that are influenced, in this case, by network constraints. The first thing to choose here is what bitrate should this video be in, right? Everybody loves high-definition videos. They're great from an engagement perspective. But if you don't have the right amount of bandwidth, you might be buffering for 20 minutes. Who's going to wait around, right? How much should you buffer initially versus buffer over time? How do you know that? You have to make all these decisions even before the first request has ever been sent. These require understanding of the network, right? So product metrics, in order to achieve the right user experience, they need to understand what are the right trade-offs to be made to account for these network constraints. Our apps are complex. Our little Facebook app does many requests. The most important one, which is very latency sensitive, is the newsfeed request. It's a JSON payload without which the customers cannot engage with our apps. Photos, another kind of request. In this case, we need to figure out, based on the network conditions, what are some of the resolutions we should be downloading at this time. There are many other requests, but to just highlight the chat and VoIP kind request, where latency, again, is of importance. But in case of the VoIP app, it also has to account for packet loss because it's built on top of UDP. So overall, the things that we have to do to understand the network are very important. APIs that are available on Android and iOS are great. They make it easy to issue an HTTP request or open a socket. But they obscure away a lot of important information that is required to understand the network, required to make decisions. Such observability and ability to control the stack end-to-end across platforms is key to operating at scale. That brings us to Proxygen Mobile. And please help me welcome Ranjit to the stage, who's going to dive deeper into our networking client. Thank you.
Hi, I'm Ranjit. I'm a software engineer on the traffic infrastructure team at Facebook. You guys can hear me, right? All right. I was told there are no questions, so finally I thought, here's an audience that doesn't heckle me. I can say whatever I want, right? So, all right. So the reason for cross-platform library is that, like Saral said, we want to reduce the feature divergence, API divergence, and performance divergence, most importantly. We want the same thing to work on both sides so that products don't get delayed on one platform. They ship everywhere at the same time. And flexibility is important. Different apps have different needs, and they evolve over time and across platforms. So we wanted a framework where we can plug and play functionality, remove what we want, and reconfigure based on network conditions changing. Right? The other thing that was important was, before you even begin to optimize, you want to measure. Right? A lot of the abstractions today that are available, for instance, client network stacks that are available today are optimized for adoption speed, not necessarily optimizing or measuring every stage. Right? So these are the constraints on us. So for inspiration, we looked at the server side. Servers solve network problems all the time. And there is this great component that powers our server-side infrastructure called Proxygen, which is a set of HTTP client libraries and framework for building this service. It's flexible and scalable network service. It's built on top of existing open source components like Openssl and Folly, a C++ library for writing these services. And it's on GitHub. You're welcome to check it out. We always welcome pull requests, so go ahead and do that. So to expand on what Proxygen does for us on the server side, here is a very simplified diagram of what happens when a client requests a resource. Right? It talks HTTP, speedy, or HTTP2. It travels to the internet, lands up on one of the reverse proxy servers. It's built on top of these Proxygen libraries. Here is a point where we do SSL termination, inspect the headers, load balance it to one of the PHP boxes, get the response back, and stream it back. Once it's been built, it has become all pervasive. We use it at the edge termination nodes, terminate the connection much closer to the user, and our CDN nodes as well. The reason is, having this component allows us to examine the traffic, what's going on, how much time does the page generation take, what is the RTT to the client, what can we do better. And a lot of custom optimizations that are very specific to Facebook go into this piece. So we thought, OK, this thing is great. Now how do we get it to mobile? Right? Apparently, it's not so easy because clients and servers differ in what they are optimizing for. Servers optimize resources over thousands of requests, whereas client has its own self-interest. OK, get me as fast as possible, optimize my bandwidth usage. Right? Then going cross-platform meant other hurdles as well. The first of these is existing lingua franca of each platform is different. It's not C, C++, but Java on one side and Objective-C. And particularly on Android, we have to cross the JNI bridge. And usually when I say JNI, not on the stage, they're followed by kill me now. Right? So, we want to minimize the number of times we cross this bridge by not copying and instead passing objects. And when we say passing objects, we are dealing with two languages that look at memory entirely differently. One is a garbage collected language. The other one is managed, right? Hand managed that way. And there are different concurrency models. One platform says, oh, execute everything on one thread, I don't care, while threads are free. The other one says, let's make one thread per request. So we have to reconcile all these differences. Then the build and debug tools on these platforms inherently evolve based on the usage, and Android and iOS are not, the primary candidate for development is not C++, right? So the absence of advanced tools makes it difficult. We had to do a lot of custom tooling. Then there are subtle architectural differences. Remember, we are taking code that was running on server 64-bit architecture to ARM now, right? And suddenly there is a counter somewhere buffering your videos, which overruns and becomes negative, and your video is paused forever. This is a very subtle bug. Nobody can find it in a reasonable amount of time. So these were the hurdles, but we crossed them. The end result turned out to be pretty sweet. So the first of them is we are building on top of open source. Right? This building blocks for this mobile Proxygen are same as what are for Proxygen, Openssl, Folly. So at this point, you might look at Openssl and dude, haven't you heard of Heartbleed or Poodle? Right? Those bugs notwithstanding, this is a primary implementation out there and undergoes a lot of scrutiny. That itself has a lot of value. Right? And Facebook is backing Openssl through the core infrastructure initiative of Linux Foundation. We want to harden this as opposed to inventing something of our own. Right? So that's the advantage of building on top of open source, but that's not the end of it. Once you take these building blocks and you're trying to build a flexible client, you want to design components that have very simple interfaces so that you can test them easily. Each does one thing and does that one thing well, so that you can combine them and build something more sophisticated. Right? That becomes clear with an example. So here's what typically, in the modern day of HTTPS, here's what happens when a HTTP request comes through, right? There are different layers. TLS, so on the far right, you see socket, right? At its core, it's something that you read bytes from, write bytes to. And everything else can be layered as an abstraction on top of it. So here's a transport connector interface. What it supports is get transport, takes a host name, address, timeout, and gives you back something that looks like a socket, right? So as you go forward, each layer is asking the next layer to do something for it and return it a transport, right? So TLS says, oh, here's a host name, a DNS. Why don't you resolve these addresses for me and give me a socket back so that I can negotiate my TLS on top of it? DNS now has a dilemma, because in a dual stacked world, you have v4 and v6 addresses returned. And in an earlier talk, you heard, if you're not doing v6, you're hurting users. So clearly, there is a choice to be made. But it's not very obvious. Sometimes v4 could be faster. So you have this happy eyeballs algorithm which runs and says, OK, let me open 2 sockets, try them out, and see which one is faster. Let me give that to the next layer. Then you have retry. In a spotty network condition, you don't want to give up with one attempt to make a TCP connection. You want to try a few times and then give up, right? So that layer functionality can be layered on as a separate layer. Now, as it comes back, happy eyeballs probably does something more sophisticated, like caching it until network conditions change, so that you don't have to do this comparison over and over. DNS will cache some more results. And TLS might do something like resuming an established session as opposed to doing a fresh handshake. So all of this complex functionality, when it's broken down into these layers, it becomes easy to handle changing conditions. So it becomes apparent when the network condition has changed. Now imagine this guy is walking with his phone from a mobile network to a building where a proxy is configured, right? So both DNS and happy eyeballs now have to be delegated to the proxy. It's no longer the client's responsibility. So instead of tearing the whole client, we say, oh, let's replace these 2 connectors with a SOX connector, and you have gracefully switched to a new condition now, right? And that is the advantage of building these simple components. You can extend that idea. It's not just at the network layer, but at the app layer also, when the request or response is streamed to you, you want to do a lot of custom processing on it. For instance, saving bytes is one of the biggest things you want to compress. Maybe you want to handle redirects or cookies, or there is this concept of application level retry. Get requests, you can retry. If there are posts, probably the app knows something about them and says, hey, here are the safe requests that can be replayed. It's a post, but you can replay. So you marked it as idempotent, and this layer can retry. So you can layer this functionality and achieve something sophisticated, right? Cool, we did all that. What does that gain us, right? So remember, now we are operating or in control about everything about the socket layer, right? So we can time all of these phases independently. And the aggregate statistics in the performance world don't mean anything. You have to look at the whole distribution. You look at the PX numbers or things like that, right? So what we want is something that looks like this. Here is a very simplified diagram of an internal tool that we use to analyze our network traffic, what goes on in the app, right? So each of those blocks have a lot of metadata attached to it, along with the time taken. So for instance, TLS can expose what cipher suits the client has negotiated and things like that, right? So there are 2 concurrent requests to fb.com. Nothing is set up yet. So all the things have to be done twice, DNS, TCP, TLS, and probably if you're in a building that has a proxy configured, probably there will be a proxy phase or happy eyeballs phase here as well, right? Then offline.net, as the name suggests, probably it's offline. The DNS goes through, and TCP tries to connect a few times and gives up. That's pretty obvious. And fb.com, again, is an interesting case, because only a few seconds back, we connected to the same domain. So DNS results come out of the cache. TCP connection is already established. There is a TLS session that can be resumed. So all you have to do is jump to the request response phase, and that's what it is. Now imagine the app fails. User is frustrated. He uploads a bug report. Now the situation becomes much clearer. You can see each of these boxes and say, hey, here is where the network has dropped off. No wonder the app did not do well, right? Diagnosing issues becomes very easy. Cool. The next part is security. Probably this is something that is non-negotiable. If you're doing anything with the client stack, this is where we cannot compromise, right? So having our own Openssl in the app comes at a cost. It obviously adds size to the app. but it gets us a lot of other benefits, right? For instance, here's a whole list, right? What happens typically is we get a vulnerability like Heartbleed or Poodle, and in the previous world, we were tied to the platform rolling that critical security fix, and that could take days, weeks, whatever that takes, right? In this case, we can roll the new app, and that has a patched OpenSSL, and you're in the clear, right? So similarly, certificate pinning. This is a great tool for avoiding or mitigating man-in-the-middle possibility, right? We have an alternate way of associating identities that works better. In case catastrophe happens and our certificates are somehow compromised, we have better support of revocation than in the past. Then cipher suite tuning. This is something possible only when you connect, when you control both ends of the connection. That's when you can really pick and choose. Otherwise, in the usual stacks, there is very little probability of negotiating the cipher suite, right? And that can be used to disable unused or broken functionality. For instance, RC4 MD5 was broken for a while in the Android world, right? So these are the security benefits, and the real reason why we do this, performance, right? So performance falls into roughly two categories in this thing, right? Apps are like browsers, so we can leverage all the techniques that were developed in the browser world and import them into the app. Apps are also not like browsers in the sense that browser has a fixed way of interpreting resources. It gets JS, CSS, and then it starts rendering, executes Ajax. But app has its own way of consuming data. It has a better idea of what the priorities are from an application level. So what we do is, one, import all the best practices from the browser world. This is things like late socket binding, where we hold off associating a HTTP transaction to a socket till the latest point, till the last point, so that a lot of other optimizations become possible. Maybe other connection becomes idle, we can predict connections, have a backup connection, things like that. So connection management in general is very good. The next one is caching DNS results, resuming TLS sessions so that you don't have to pay the cost of TLS handshake every time. The other advantage is, like I said, apps have a very good idea of what resources are more important, and that relative importance, we can plug that into a scheduler and say, hey, fetch these resources before anything else, so that the rendering starts much earlier. The third advantage is really great. You can work around bad TCP behavior when you control all the layers, right? Or in this case, absent TCP behavior in the example I'm about to give. So in the Linux world, there was this technique called tail loss probe, which existed for a long time to deal with packet loss better. So the idea is you retransmit some of the packets at the end of a short packet burst with the assumption that the tail is what is getting lost, right? And that used to work well for packet loss. But the Linux kernel and Android kernel lag by a fair bit. So we thought, OK, let's work around this problem at the higher layer by sending what's called a speedy ping frame. It's just a ping frame, like it doesn't do anything. But what it does is it converts the real data to non-tail data. You have some additional data, but now the real valuable data is in not tail, right? So it still remains in the fast retransmit mode. So you have basically simulated tail loss probe by doing an application level trick, right? The next set of optimizations is what I would call weird science, right? The reason it is weird is it is subject to empirical evidence. This is like, we measure things because we control both sides, and subject to assumptions like, OK, we own both sides, right? The first example of that is this HPAC extension for Speedy. HPAC is a header compression protocol that was proposed as part of HTTP2, which was a later protocol, which it's a later protocol coming after Speedy, right? But HTTP2 was evolving. We did not implement HTTP2 yet. We had to test it and all that stuff. Meanwhile, the existing compression algorithm on Speedy was zzip. And zzip with Speedy was susceptible to this crime attack. It's a security attack. And we had to turn off compression. And that's a huge deal, because now you're sending more bytes over the wire. Now, it's wait a minute. So we control both ends of the connection. So if the server understands a hybrid protocol, it's OK, right? So we advertise HPAC over Speedy, and we created this Franken protocol that is not there out there, but can be understood by our servers. So we have header compression back on old Speedy. Asynchronous DNS lookup is another bigger, another optimization that is possible because we make these assumptions. We are talking almost always to Facebook servers. A browser, is talking to a bunch of domains. It has to respect TTLs on the DNS names and things like that. But for our client, it's totally a valid assumption to think that, hey, a few minutes back I got a Facebook IP address. Probably it's alive now. Even though TTL has expired, let me fire off an asynchronous request and update my cache, and I keep using this old address. Right? That gets our DNS lookup time almost to 0. Right? And that's a big advantage. Now, when the app misbehaves, in the desktop world, if something goes wrong, network doesn't seem to work, the go-to tool is traceroute. We traceroute then and there. We see how far the packet gets, and we can diagnose a lot of issues. In app world, there's no parallel. This was not solved at all. But now, on both platforms, traceroute can be done without having elevated privileges. So we bundle our own implementation of traceroute into both these apps. And on every bug report, we take a traceroute then and there so that you reflect the conditions, you have a full report of what network looks like, and we attach it with bug report. So for a person who is looking at this bug, it becomes far easier now to triage whether it's an app problem, or was a network problem, or was it something in between. Right? The same goes for network quality in bug reports. Right? We want to measure what is the bandwidth, what is the packet loss, what is the RTT, is it affecting the app behavior? So having this quality reported in the bugs helps a lot. So controlling every phase of the connection allows us to examine all these attributes and report it back to the server. So in summary, these are the thoughts I want to leave with you. Cross-platform library, solve at once, and in our case, it's actually solve on the server side, and then it's available everywhere, so we can leverage that. Flexible and scalable because of those modular components. Now you can actually gracefully switch between various network conditions, provide different things to apps, and instrumentation is important. So that's the deal. So hopefully you have learned a lot from our experience. Thank you.